Hello, let's do the New York Times Hard Sudoku for February 13th, 2026. There's a link in the description if you'd like to try the puzzle yourself, and I'm going to get started right now. All right, we got this 2 and this 7. I'm not seeing anything with the 2. Oh, I do see one thing. These two 2s look in. This 2 looks in. All right, I do see something with the 2. The 2's right there. These two 2s look in here, putting a 2 in one of these two. This column's down to 4 digits. I'm just going to pencil it right away. We need a 3, 5, 7, 9. So this can't be 3, 7, or 9. So this is a naked 5. And then this is 3, 7, 9. Bottom one's not 9. And this one's not 7. Oh, this isn't 3 or 9. So that's a naked 7. So we're left with a 3, 9 pair here already. I'll deal with the other place digits in a moment, or when I get to them. But I'm going to deal with this 5 right away. So the 5, is there anything to do with the 5? I'm not seeing anything immediate to do with the 5, actually. All right. What about this 7? 2 7s look in. All right, 7's in one of these two. So what we've found here is what's called a hidden pair, because what these corner marks mean is that in one of these two cells, we have a 2, and in one of these two cells, we have a 7, guaranteed. And so if one of them's a 2 and the other is a 7, there's no room for anything else. So the way we follow up on a hidden pair is we think about what did we just remove from these two cells, and how does that affect the box? How might that affect the row or their columns? I doubt it affects the row or the columns very much, but let's look at the box. So just because they're almost empty. So now they already couldn't have been 1. There or it can be 2, 3, 4. So 5 was removed. We have this 5 looking in, this 5 looking up. So that means 5's in one of these two. So because 5 was removed from here, we've now have pointing 5's in this box. And that puts a 5 in one of these two. All right. So that was 5. They can't be 6 now. I don't see anything with 6. 7, no. 8. 9. All right, we have this 9 looking in, this 9 looking up. So 9's in one of these two. That's also going to point. This 9 looks in, putting a 9 in one of these 3. All right. So that's our follow-up from the hidden pair. I'm also noticing these two digits must be limited because they're not the 3, 4, they're not the 2, 7, and they're not the 5, 9. That's 6 digits that they aren't. I'm just going to look at the whole row, though. We need a 1, 4, 6, 8. 1, 4, 6, 8. So these aren't 4, so these are 1, 6, 8, and that's not a 1. This can't be a 1 or a 6. This is 4, 8. I think this can be any of them. All right. Anything else? What was I doing? 5, 7. It was this hidden 2, 7 pair. All right. So we got this 7. How about vertically? 7's one of these 3. All right. This box, we've got the 1, 2, 7, and 9. The 1 actually is in one of these two. That points in here with this one, putting a 1 in one of these two. Nothing horizontal. The 2, no. 7, 2 7s looking here, putting a 7 in one of these two. We could be forming a triple here, but at the very least we can pencil these two down to at least, down to at most 3 digits. So they can't be 1, 2. They could be 3, not 4. They could be 5. This one can be 6, but not this one. And then, not 7, not 8, not 9. Yeah, so this is what they're down to. 3, 5, and 3, 5, 6. All right. I don't see anything to do with that immediately. We do have, so that was the 7s. We do have 2 9s looking down. This 9 looks in, placing this 9. These 2 9s look in here, putting a 9 in one of these two. This column's down to 4 digits now. We need a 3, 4, 5, 6. This can't be 5 or 6. So this is 3, 4. This can't be 5. We have the pointing and claiming 5. So this is 3, 4, 6. All right. I think that's it for this box. This box, we have the 3 and the 4. I think we've found what we can from that. I guess the 3s we didn't do. 3 is one of those two. Okay. I think we're going to move on to the next band. So we got 4 and 6 here. We have the 2 4s looking in. This 4 looks down. Puts a 4 in one of these two. How about the 6? Okay, 2, 4, 8, and 9. These two twos, no. 4, 8, 9. I'm not seeing anything else to do with this box. I think I'm just going to move on. This one looks down, one looks in, puts a 1 on one of these two. Oops, so that points up with this one. One's one of these two. All right. So 3, 4, 2, 7, 1, 9. So this is limited because it's none of those digits I just said. So it's not 1, 2, 3, 4. It could be 5. It could be 6. It could be 7. No, it can't be 7. It could be 8. 5, 6, 8. Okay. For what it's worth, I think we just want to move on to the last band here. So I've got 1, 3, 8, 9. Oh, I'm seeing our standard New York Times trick. So the way this works, I've actually explained this fairly recently, but I'll explain it in the same way because I think this is a very helpful way to explain it. So we've got the 1, 3, and 8 in this box. So what I'm going to do is I'm going to take the digits 1 to 9, and I'm going to split them into 3 equal-sized groups. But I'm not just going to do 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm specifically picking the 3 digits in this box and the 3 digits in this row. So the 1, 3, and 8 are what I'm going to call the green group. The 5, 6, and 9, notice that doesn't overlap with 1, 3, 8 at all. I'm going to call that the purple group. And then I'm just going to make a orange group, which is the other digits. That's going to be in this case, the 2, the 4, and the 7. Now I've explicitly picked them to be the 3 givens in this box and the 3 givens in this row that aren't in this box. And it's the 3 givens that aren't in this row versus the 3 givens that aren't in this box. All right. So we know that there's exactly 3 greens, 3 purples, and 3 oranges in every row column box because I've split up the digits and I haven't missed any digits. And so we have to color every cell green, purple, or orange, and I can't exceed 3 in any row column or box. So this box already has 3 greens in it. So these 3 can't be green. So where do the green go in the row? You can't make these both green and purple. There's no overlap between the groups. And so these are the only places green can go. So we ought to fill all 3 of these with green in order to get 3 greens. And now this row already has 3 greens and 3 purples, and so the remaining have to be my orange group. And then now this box has 3 greens and 3 oranges, so the remaining have to be the purple group. Now we know what digits go in green and orange and purple. So in these greens, the digits are 1, 3, and 8. So this can't be a 4. 4 is orange, not green. So it actually can't be orange. It must be green. It's a 3. And then this is left as a 1, 8 pair. Now that 3 has severe consequences here. That's a 5, that's a 6, that's a 4. That places an 8 up here, giving us the 6 and the 1. All right, at the very least, we get all that. I'm going to follow up a little bit in just a second. I've got to remember I got all these digits. But I want to finish filling these. So the purple digits are the 5, 6, and 9. That's not 9. And then the orange digits were the 2, 4, and 7. So this is a 2, 4 pair. Okay, so we've completed that New York Times trick dealy. It gets you all of that every time. What way we notice it is 3 digits in a box that avoid a row, and 3 digits in the row outside of that box that are completely different from these 3. All right, and you always get all of those deductions from that because you can just make that same coloring argument. All right, so we got a bunch of digits here. Let's make sure let's finish this row for perhaps. That's a 4. That gives us the 2 and the 4 down here, leaving just a 1, 8 pair behind. Anything else with that 4? No. Did we get the 5? No, we got that 5 earlier. The 8. We have 2 8s looking down, putting an 8 one of these 2. Did I get this 2? Maybe, but I don't think it does anything. This 4. We do have 2 4s looking down, so that's a 4 in one of these 2. How about the 1 and the 6? We do have 2 1s. We got that. The 6. We not do anything with 6s? Okay, 6s in one of these 2. Because we got this 5 and 6 too, I believe. I am not seeing anything to do with 5. How about these 3? So we need a 1 here, a 7 here, and what's the other digit? A 3. And then up here, we need a 3, 5, 6. That's not a 6. So 6 is one of these 2. All right, yeah, I missed these 2 6s. I don't know how. This column is just down to 4 digits, 1, 3, 4, 5. They're not 3. So these are 1, 4, 5. That's not a 1. Okay, I'm seeing something I'm not going to use. But when I see more advanced techniques, I do like to point them out and explain them. It's just I usually aren't not looking for them, where they're generally, because they're advanced, they're harder to spot. But this one I did just spot, so because they're right next to each other, which helps. What I found is called an X-wing. I think if you were to make a dividing line between basics and non-basics, which something called advanced, sometimes they're categorized like mid-tier and advanced and extreme and whatever. But anyway, every technique I go over is generally considered a basic technique that are required for New York Times Hard. New York Times Hard never requires anything else, and so we call those the basics. And then X-wing is usually right at the cusp of not being basic anymore, but it's probably the easiest of the basics to understand, of the non-basics to understand. Anyway, that's a long tangent. So there are a lot of ways to explain the X-wing. I'm going to pick 3 of them because I think this puzzle is not going to take very long, so I can spend a bit more time explaining. So if you don't like learning about all this stuff or you already know it, feel free to skip ahead. But many of you may find this interesting. 3 different ways to explain how the X-wing works in increasingly more generic terms that you can then apply more generically and kind of explain more techniques that way. And so it kind of expands your ability to, it adds to your toolkit for how to analyze a puzzle, which I find that kind of neat. All right, it's also just neat on its own. Anyway, the most basic way to explain an X-wing is that in this column, we have limited 3 to these 2 green cells. Notice 3 can't go anywhere else. In this column, same thing. We have limited 3 to these 2 green cells. Now, these two, the 2 places for 3 in this column and the 2 places for 3 in this column happen to share rows with each other. And so I need to place 2 3s. I need to place a 3 in this column and I need to place a 3 in this column. But I can't do it like this because that's in the same row. And I can't do it like this because that's in the same row. So my only choice is to either do it here or to do it here. And that's where the X-wing gets its name. You can kind of draw an X. It's either in this diagonal or it's in this diagonal, making an X. And so that will be true. One of these must be true. Either these are both 3 or these are both 3. We don't know which one is true, but what we do know is that means that the rest of the rows cannot be 3. Because if they were, then we would not be able to place 2 3s in the green. All right, if I try to put a 3 here, neither of these are 3 now. I still need a 3 in this column, and I need a 3 in this column, and they both end up here. That's bad. So we can eliminate 3 from all of these cells. Again, I'm not going to, because I don't like depending on advanced techniques in my walkthrough solve. But if you would like to use it, feel free. Like if you spot an X-wing, just use the thing. Like if your goal is to solve the puzzle and have fun, like that's pretty fun. All right. That's one way to explain it. That's kind of the most straightforward X-wing explanation. But it's hard to expand that to be like, how do we increase something to how do we discover more techniques now that we have that tool? The next thing we can do is it's called the base set cover set. So what we're going to do in this case, a set is going to be any place, any 9 cells that require 1 to 9 ones each. So a column, a row, or a box could be a set. And so the base sets are going to be these 2 columns. The base set these are the 2 columns in which we need to place the digit. And what we're going to do is we're going to, within the base set, again, I'm going to just highlight the places 3 can go in our base set. So I'm trying to think about the best way to kind of describe this, but here, let's do it this way. Let's just make the green as our base set. Now what I'm going to do is I'm going to use rows. So since these are made out of columns, I'm going to use rows and I'm going to try to cover every instance of 3 within green, within our base set. I'm going to make that purple. So I'm going to highlight this row in purple. That covers 2 of our possibilities for 3. And I'm going to highlight this row in purple, and that covers the other 2 places where we can put 3. So if you, then we call the purple our cover set. So we have managed to cover everywhere that 3 could go in green. If you manage to do so in the same number of cover sets as you have base sets. So we have 2 base sets. And so I was able to cover every place 3 can go with 2 cover sets. And since those are equal, that means that any place in the cover set that is not green cannot be 3. And so we can, again, eliminate 3 from, it's the same cells. We eliminate 3 from all of these cells, thereby placing this 3, for example. So that's another way to explain it. And if you think about it, it's actually a similar explanation, but it's a bit more generic, where because my cover set has exactly 2 3s in it. It's 2 rows. 2 rows have 2 3s. Because my cover set has exactly 2 3s in it, and I've managed to cover every 3 that exists in green, which is 2 of them, because we know green has 2 3s in it. Therefore, green is going to steal all of those 3s from purple. I don't know a better way to say that, but I have covered every 3 in green with purple. Purple has exactly 2 3s in it, and I've covered exactly 2 3s. Therefore, the rest of purple can't have any 3s in it. All right, so that's explanation 2. And that lets you, as you can see, you'd be able to expand that to 3 rows and 3 columns, or 4 rows and 4 columns. Or you could even start saying, oh, what if I use 1 box and 1 column and then 2 rows? Can I do it that? Answer is yes, in certain situations, things like that. All right, so that's base set, cover set terminology. And our final terminology we're going to use is called set theory. Set theory stands for set equivalence theory. So this is how this works. And it's going to actually remind you of the base and cover set, but it's done a little bit differently. So what I'm going to do is I'm going to highlight these 2 columns in green. And what I'm going to say is green has exactly 2 sets of the digits 1 to 9. Why do I know that? Well, it's 2 columns, and each column has 1 set of 1 to 9. And so if I have a bag in my left hand and I take 1 column, a column is going to be 1 to 9. Say I take tiles that are 1 to 9, I stick them in that bag. And then I take another set of 1 to 9 tiles and I stick them in that bag. My bag now has 2 of each of 1 to 9. So that's what I've done. And we call that the green bag. All right, now I'm going to highlight 2 rows in purple. And that's my purple bag. And purple bag also has 1 to 9 twice each. So, we take 1 to 9, put it in the purple, take another 1 to 9, put it in the purple. That's exactly what we've done by highlighting this row and then this row. So my 2 bags have the same tiles in them. They each have 1 to 9 twice each. So if you imagine, if I were to remove a 1 from the left bag and then also remove a 1 from the right bag, they'd still have the same tiles in them. As long as I'm removing the same digit from both bags, I have kept them equivalent. That's the equivalency in set equivalence theory. So what about this cell here? This cell here, so I guess a simple example would be if I remove a 1 from green here and a 1 from purple here, green and purple are still the same as each other, right? So that's one way I could do it. But I could also just remove this cell where they cross, because by definition, it's in both green and purple. Whatever digit it ends up being, I don't know if I'm removing a 3 or a 5 from both, but I know that they're still the same as each other, because I've removed whatever this digit ends up being in the solution. And it was already in both because they're crossing each other. And so I can do that to all of these. And by removing these, basically where they overlap, I have preserved the property that green and purple have the same digits as each other. I wouldn't be able to enumerate them to you because I don't know what these cells are, but I do know, I can tell you that if a digit appears in green, then it also appears in purple and vice versa. They are equal sets. So if you'll notice, I no longer have a 3 in green. I've got all of these digits in green, and not a single one of them is a 3. So if I don't have any 3s in green, how can I have 3s in purple? The answer is I don't. They have the same digits. And so all of these purple cells, if I thought they could be 3, no, they can't. So this can't be 3, this can't be 3, this can't be 3, etc. We can do those eliminations. So those are 3 ways of looking at the same thing. I hope that was worth the about 9 to 10 minutes that I spent explaining it. I think that's a nice exploration of advanced techniques just thrown into the middle of this puzzle that you'll randomly find as a little gem. All right. So let's continue. I've, of course, completely lost the plot, but let's see. Let's just scan this band again. What was I doing? Oh, right. I was on this box because I did the New York Times trick. Excuse me. This can't be 4, so this is 158. Oh, it's not a 1 either. Okay. Do I have any more buddies worth mentioning? I have 2 2s. What's a 2 in one of these 3? All right. I think that does it for my initial scan. So, and by the way, I didn't eliminate those 3s that we were talking about because I don't use those techniques in these walkthroughs. All right. Anyway, I'm going to scan row by row, and I'm going to see if there's anything worth marking that I might have missed. So let's see. Oh, actually, I'm going to do this triple first. This is a triple. We have the 2 7. All these are kind of known. So what's the other digit? 7? No, 9. It's oh sorry, it's 5 8 9. I did know all the digits already. And so that leaves 3 digits to the left here. These are 3 digits go in here. It looks like it's 1 3 6. It's not a 3. All right. This row here, we have the 2 7 pair, so there's 4 digits here. They are the 3 5 6 7 8 9. Oh no, not 7. 3 5 6 8 9. 3 5 6 8 9. All I see is these 3. Oh, they see 5 as well. So this is 6 8 9. I think this can be 3 6 8 9. All right. How about this row then? We need a 1 2 3 7 8. These can't be 1. So these are 2 3 7 8. These both can't be 3. So these are. Sorry, I think I missed a digit. What did we need? 1 2 3. So these are 2 7 8. Okay, 2 7 8. 3 2 3 7 8. This can't be 2 or 3. So this is 1 7 8. All right. I don't see anything else there. How about this row? I need a 3 5 7 8 9. This is 7 8 9 because it's not 3 5. I don't think I can do anything with these 2. So far, not a whole lot of good coming out of this. How about this row then? We need a 1 4 5 6 9. Well, these can't be 5 9. What did I say? 1 4 5 6 9. This can't be 1 1 6 for the column and 5 9 for the box. 1 4 5 6 9. So this is a naked 4. This can only be 4, amazingly. So that's a 4. Sneaky hidden single there. 1 5. So this can't be 5 or 9. So this is 1 6 only. All right. It's these 2 digits. Can I follow up on this 4 maybe? Yeah, I think 4 is placed right here, and then that places our 6. That gives us the 1 and the 5. Places the 5 in this box. We get the 8 and the 1 here. That's an 8. All right, the 5 looks up, giving us the 3, the 5, and the 6. This is our 9. We get the 1 and the 3. This is a 3 now. That's a 1. So our X-Wing resolved. I picked this diagonal. All right, that's 7 and that's 3. That's 7 and that's 1 and that's 8. We get the 6 here. These aren't 8, so this is a 3 for the row. That's not 9. Sorry, not 9. It's not 7. That's not 8. All right, let's get this digit. It looks like we just collapsed it. That's 8. We get the 9 and the 6. Sure, I'll just do these 3. We need a 2 6 7. Okay, the 6 can only go here. 2 7 pair, 8 9 pair. Oh, what's this? What's the box need? The box needs a 2, 5, and 9. So this is the 5. This 2 looks in. That's 9. That's 2. We get the 8 and the 9. We get the 5 and the 8. That's a lot of 2 7s. All right. What's this going to be? 5? No. Oh, shoot. Did I make a mistake somewhere? I must have gone too fast somewhere. Let me back up a little bit. Something was too fast. I think this was fine. 5, 5, 8, 1, 8. I got the 3. I got the 5 and the 6. I got the 9. That's fine. 1 and 3. I got that 3. I got that 1. We get the 7 and the 3. We get there was this 7 here. That I should not have placed because there were 2 places for 7 in the box. Okay. Recovered from a mistake again. All right, so that's 1. It was just going too fast. This is 6 or 8. That's not 8. That's not 8. That's not 3. This is a 3. These aren't 5. All right. What was this triple again? I think we needed a 6. Yeah, we needed a 6 here. That's still true. And then this is 2 and 7. All right, we have this 2 7 pair. 2 7 pair here. So this is down to 5 8, but it's not 8. So that's 5. That's 8. We get the 9 and the 5. That's not 9. What's this digit? This is 9. Okay. Over here, I need a 5 7 8. This can't be 5 or 7. So that's our 8. This is the 5 for the row, and that's a 7. We get the 2 and the 8. That's a 7. So yeah, we knew that this wasn't going to end up 7 because we broke the puzzle doing it. That's 6. That's 9 and 6. That's 7 and 2. We get the 2 and the 7 here. All those 2 7s resolved. 2 and 9 are left. That's 9. That's 2. All right, we finished. Obviously, I spent what, like 9 or 10 minutes explaining the fun stuff, the X-wing, and then base and cover set, and then set theory. Getting more and more kind of generic as we go. All right, cool. Well, that's it for this puzzle. Let me know how you did. And if you enjoyed this, why don't leave a like, subscribe, and a kind comment below.